Let's start the presentation. I think I'm the last one, the presentation schedule today. I'm Seunghun, and I'm very excited to share my research result with you. This is my second visit to Hack in the Box as a speaker. Thank you for inviting me again. In this presentation, I'm going to talk about the lightweight hypervisor-based kernel protector, Sandbox. I'm a senior security researcher at NSR of South Korea, and I was a speaker at Hack in the Box last year and Black Hat Asia in this year. I'm also an operating system and firmware developer and an author of a book series titled 64-bit multi-core operating system, principles and structures, volume 1 and volume 2. My goal of this presentation, first, as I mentioned earlier, I share my lightweight hypervisor-based kernel protector, Sandbox. Sandbox consumes less resource than previous researches, and I made it from scratch. Second, I also share lessons learned from deploying and operating Sandbox in real world. Many excellent researches are only focused on laboratory environment, so when you try to apply them in real world, you could have many problems. I have been operating Sandbox since last year, and I share my experience. Third, I introduced the future plan, Sandbox version 2. Sandbox version 2 can support ARM and x86 platform concurrently. This is a contents page. First, I will tell you a background of my research, and second, I will tell you how I design and implement the Sandbox. Third, I will share the lessons learned and show a demo. Finally, I will introduce future plan and some of my presentation. As you know, Linux kernel is everywhere from servers and PCs to mobile devices and connected cars. And Linux kernel suffers from rootkits and security vulnerabilities. Unfortunately, devices which use Linux kernel could share these security threats, and the security threats often combine with other threats to take control of a system. Although you already have a protection mechanism in kernel level, fundamentally, the mechanism could not protect kernel from these security threats, and the mechanism often easily bypassed and neutralized by kernel object hooking and direct kernel object manipulation technique. Therefore, protections need an even lower level. I call this link -1. This is well-known rootkits and a list of kernel objects which are modified by rootkits. Well-known rootkits normally change codes, system tables, function pointers, process list, and module list. The descendants of well-known rootkits are also have similar patterns. The exploits tend to get root privilege, and the rootkits tend to hide their malicious behaviors. As you know, the attacker needs root privilege to load rootkit. Therefore, I assume that the attacker already has the root privilege using exploits, and in this presentation, I only focus on rootkits. To take the higher ground than kernel level, I leverage virtualization technology in processor. Virtualization technology separates a machine into a host, secure world, and a guest, normal world. The host has link -1 privilege and can freely access and control the guest. Intel VTX and AMD-v ARM TrustZone are typical VT-equipped hardware. This is traditional architecture leveraging virtualization technology. The host monitors and controls the guest through the virtualization technology, and the malwares of the guest cannot move to the host because of virtualization technology war. Unfortunately, I'm not the only man who finds the benefit of virtualization technology. There were so many researches using it for protecting kernel from malwares. So it seems that I did not need to research on this field, but after studying about previous works, I thought that they look like these objects. Okay. Dragon, and Griffin, and D1 link. Can you guess the common points of these objects? Anyone? The common point? Yeah. The common point of this object is the myth I heard and knew about them, but I cannot find in real world. I agree that previous works are excellent and I want to use them, but I don't know where they are. If you know about them, please email me. Okay, thank you. And so I think that they become the myths because of these reasons. First, many researches have preconditions which are how to be prepared in real-world environment. They change kernel code or hypervisor code directly and need well-known hashes of loadable kernel module and kernel data, secure VM, and so on. Second, many researches consume much resource. They run OSes in each word and consume many CPU cycles to introspect the guest because of semantic gap. Semantic gap comes from the gap between logical address of the guest and the physical page of the host. The host can only access physical page of the guest. Therefore, if the host wants to introspect the guest object, the host should convert the guest logical address to host physical page. This behavior causes many table traverses and consumes much resource. In conclusion, previous researches are not suitable for real-world environment. As you know, real-world environment is totally different from laboratory environment. And you even don't know the actual environment before your software is installed. So we feel like that. Real world, this is a real world environment like Serengeti. So I think that practical and lightweight mechanism is needed for real world environment. And I started to make it from scratch 3 years ago. As I mentioned the previous security conference, I should not have started because it has been a hard work. So many problems are there, and I should solve the problem alone. So I regret now. Anyway, this is design goal of my kernel protector. First, I focus on lightweight rootkit detection and protection mechanism, and I also focus on small memory footprint. Second, I try not to modify code directly for deploying, and I design the kernel protector to load anytime. Design page. This is shadow play you did in early childhood. Yes, everyone knows about this. The bulb sends light to the actors, and the shadows of actors are reflected in a screen. Over there, my coworker and I watch the shadow and understand the story of shadow play. One day, suddenly I realized that this architecture could be applied in security. Can you guess how can apply the? Yes, I will show you. The verb is link-1 protection mechanism. I call this LightBox, and the actors are activities in OS, and I am the security monitor. I call this Shadow Watcher. So I named my kernel protector Shadowbox because I was inspired by the shadow play. This is a more detailed architecture of Shadowbox. LightBox, lightweight hypervisor, creates a guest which run OS in it, and creates a host which share Linux kernel with the guest. Conceptually, LightBox sets read-only permission to most part of the guest kernel and set read-write permission to the host kernel. Therefore, Shadowbox shares the Linux kernel between the host and the guest. The kernel modification of the guest can be prevented and cannot affect the host kernel. Shadow Watcher over there, security monitor, controls and monitors OS in the guest using LightBox. LightBox lightweight hypervisor isolates the guest from the host by using memory protection technique in VT. But LightBox shares the kernel between the host and the guest. Therefore, it has small memory footprints. Due to sharing kernel, the LightBox easily knows the logical address of a kernel object and easily convert the guest logical address to host physical page. In some case, you just use bird-to-physis kernel function to find the physical page not to traverse the page table. So LightBox has narrow semantic gap. Additionally, LightBox is a loadable kernel module, so it can be loaded anytime. Therefore, you can load it when you need it. Shadow Watcher monitors the guest by using LightBox. It uses event-driven ways and periodic ways to monitor the guest. Event-driven way is used for checking static, immutable objects such as code, system table, and IDT tables. Periodic way is used for checking dynamic and mutable objects such as process list, loadable kernel module list, and function pointers. This is summary page of design. So, what can Shadowbox do? First, Shadowbox protects kernel from static kernel objects attacks. I defined static kernel objects are immutable in runtime. Therefore, static kernel objects attacks can be code modification attacks and system table modification attacks. Second, Shadowbox protects kernel from dynamic kernel object attacks. I defined dynamic kernel objects are mutable in runtime. Therefore, dynamic kernel objects attacks can be process hiding, module hiding, and function pointer modification attacks. From this page, I will show you how I implement Shadowbox. As you know, normally implementation part has so many detailed information. Therefore, I share core information of Shadowbox because of the time. If you want to know more detailed information about this part, please check my paper. As I mentioned earlier, Shadowbox is a loadable kernel module, and Shadowbox is loaded after starting Linux kernel. Therefore, because of this boot sequence, I use another mechanism, secure boot, to ensure integrity of boot process before Shadowbox. After secure boot and Shadowbox are loaded, LightBox poses the OS and prepares an environment for virtualization. After that, it separates the guest from the host, and LightBox resumes the guest OS. Lastly, it starts Shadow Watcher. Shadow Watcher monitors the guest. After Shadowbox is loaded, all processes run within the guest, not the host. Static kernel objects are immutable. Therefore, static kernel objects protection uses the physical page protection technique. To protect physical page efficiently, EPT, as known as Extended Page Table in Intel VTD, and DMA remapping reporting table, as known as DMAR table in Intel VTX are used. I show you EPT first and DMAR table later. Like this, EPT maps guest physical address to host physical address and sets new permission. Shadowbox sets read and execute permission to static kernel objects like this, and I call this rocking. Shadowbox sets no permission to itself. I call this hiding. As you know, As you know, Rootkit can modify permissions of page table in the guest, but the guest cannot change the permissions of EPT. So, as a result, Rootkits cannot modify the static kernel object. This is a detailed view of memory protection. Left part of the page shows address translation between guest logical address and guest physical address. Right part of the page shows address translation between guest physical address and host physical address. If rootkits infect the system, they attack physical page directory or page table in the guest to change codes and system tape like this. This is typical attack. But permissions of EPT overrides permissions of guest physical page like this. Therefore, these attacks are prevented by EPT. This is another memory protection technique using DMAR table in Intel VTD. DMAR table is more complicated than EPT. However, basic structure and concepts are same as EPT. This is DMAR table, and the DMAR table maps DMA address to physical address and sets new permission. LightBox sets no permission to static kernel object, and Shadowbox for preventing DMA attacks. DMAR table can be prevented by EPT, so LightBox locks DMAR table to prevent unauthorized modification. Dynamic kernel objects are mutable, therefore, Shadowbox cannot use memory protection technique. So instead of it, Shadowbox monitors dynamic kernel objects and check them periodically. Process and module lists are typical dynamic kernel objects, and rootkits modifies the list to hide themselves. To protect list like this, Shadowbox uses hardware breakpoint to on create and delete function of process and module. When the lists are changed, Shadowbox catches the event and synchronizes list in it. Then it compares list of the guest with a list of Shadowbox periodically using VM preemption timer. Function pointers could be also dynamic kernel objects, and rootkits modify them to hide themselves and do malicious behaviors. To protect function pointers, Shadowbox check if they point to the valid kernel address space or not periodically. The concept of Shadowbox is to protect loaded kernel, and this means that function pointers should point to the inside of kernel code over module code. If the function pointers point to the outside of them like this, for example, module code which is loaded after Shadowbox, they are invalid function pointers. Static and dynamic kernel object protection are important, but for ensuring operating system integrity, interactions between kernel and user privilege should be also protected. x86 processors has many privilege-related registers and system tables. Therefore, Shadowbox protects them using VT and memory lock technique. To be honest, these are minor techniques, so If you want to know them more, please check my paper. And okay, this is a result of well-known rootkit detections. The result shows that Shadowbox can detect all of well-known rootkits successfully. And next page is the performance measurement. This is a result of performance measurement of prototype. I used test machine which has Intel i7 4790 CPU and 32 gigabyte RAM and 512 SSD for measurement. Spec, parsec, and kernel compile results shows that from 1% to 10% overhead in comparison with bare metal machine. In kernel compile case, which has well-mixed I/O jobs and CPU jobs, 5.3% in single-core processor environment and 6.2% in multi-core processor environment. I think these are reasonable overhead, and these overhead do not affect user experience. All right. So lessons learned and demo. I think these are the highlights of my presentation. So when I finished this to implement prototype of Shadowbox, I was proud of myself and I thought I was ready to launch it. So courageously, I deployed Shadowbox in real world and I met the beast of real world, such as you know, the false positive, slowdown, and system hang, and etc. Previous researches did not tell me something important, and I have struggled against the beast alone. So that was a very hard time. These are lessons learned from deploying and operating Shadowbox in real world. Lesson 1. Code area in ring scanner is not immutable. Previous researchers assumed that code area is immutable, but it is not true. As you know, Linux kernel has a config jump label option, and this option is set by default in major Linux distros. If this option is set, Linux kernel patches itself on runtime frequently, and this causes conflict with kernel protector. So, one solution of this problem is that you add exceptional cases for mutable code page. But this may cause another security problem. Therefore, I recommend, if possible, turn off config jump label option and rebuild your kernel right now. Lesson 2, cache type in EPT is very important, and you should set cache type carefully depending on physical page type. Previous researches only focus on page permissions of EPT, but EPT has cache type field for page, and you should also consider setting it. Every system has its own memory map, and memory mapped I/O area should be handled carefully. Memory mapped I/O area interacts with the hardware. Therefore, the data written in this area should transfer to hardware immediately. Because of this reason, memory mapped I/O area are set uncacheable type. If you misconfigure this cache type, it's the beast from the hell, such as the system hang, slowdown, and some undetectable errors. So, solution is that you set uncacheable type to all physical page by default, and set LightBox type to system RAM area. System RAM area are typically used for code and data, and these should be set LightBox type for system performance. This is the memory map of my test machine. It shows many information about memory area and almost memory area except system RAM are memory mapped IO. Yeah, so many memory mapped IO. So set cache type of EPT depending on system memory map like this. Lesson 3. Multi-core environment is very complicated. Each core modifies process list and module list concurrently. When hardware breakpoint exception or VM preemption timer interrupt occurred and Shadowbox tried to check them, other cores could be changing them already. Therefore, you need a mechanism for synchronizing this data. Solution is that you use task list log and module mutex of the guest for synchronization. So now I have been operating Shadowbox in real world successfully. As a matter of fact, Shadowbox is not perfect because it has some compatibility issues. But I have been upgrading Shadowbox for years, and I will continue to update Shadowbox. Oh, all right. I will show some demo videos. I prepared 2 videos. Wait a second. All right. Okay. Okay. The first demo shows typical attacks of rootkits. Demo machine has only kernel-level protection mechanisms such as light protections, and the rootkit can utilize the mechanism and do malicious behaviors. The attacker prepared the rootkit. As you can see, the rootkit is in rootkit directory. And now the attacker opens a backdoor. A simple command. Many people use this command. And however, this is not perfect because the user can find the process in process list like this. The attacker loads the rootkits to hide the backdoor process. For our research, I upgraded Odoro next generation rootkit to support lessened kernel version, and I also added a new horrible logo. Yeah, I'm scared. Yeah. Finally, the backdoor process is invisible now. And the attacker hides the rootkit directory for perfect crime. This is the command, and the command is finished successfully, like this. The file is hidden, and after that, rootkit directory is also invisible. All right. So the remote attacker, as you know, do everything through the backdoor port. The remote attacker can connect the backdoor port and he can control the victim PC. As you can see, he got the root privilege and got the shadow password from the PC. Yeah, this is typical demo. And the next one is a slight different. Wait a second. All right. The second demo is almost the same as previous demo, except Shadowbox is learning. The user prepared Shadowbox, and I mentioned earlier, Shadowbox is loadable kernel module. Therefore, the user can load Shadowbox using insmod command, like this. Now, Shadowbox is activated, And the kernel protection mechanisms such as static and dynamic kernel object protections are working. Oh, yeah. As same as previous demo, the attacker also prepared the rootkit. And the rootkit is in the rootkit directory. All right. And the attacker is opening a backdoor. And the process is in process list. And finally, the attacker loads the rootkit to hide backdoor process. But the rootkits cannot be loaded, and segmentation faults occur because of shadowbox. Shadowbox light attack information in kernel log. First, shadowbox detected memory attack of a static kernel object like this. These are address of static kernel object. And second, shadowbox detected hidden process backdoor. Yes, over there, backdoor is hidden. And finally, shadowbox detected hidden module like this, other next generation, other NG. As you have seen, shadowbox can protect your PC from rootkits. Future work and conclusion. Future work. This is current status of shadowbox. And this is next step of shadowbox. I have been making shadowbox version 2 for ARM, and I have almost finished it. Shadowbox for ARM platform shares the architecture of shadowbox for Intel platform. Typically, ARM processors are less powerful than desktop processors, and ARM processors are used for mobile environment. Therefore, shadowbox for ARM has new features such as workload concerned monitoring mechanism and remote attestation for device status check. Wait a second. Yeah. This is simple architecture of shadowbox for ARM. Shadowbox for ARM uses open source trusted execution environment which follows the TEE specification of global platform. Samsung and Qualcomm also follows it. Therefore, the architecture of shadowbox version 2 can be ported various TEE. Oh my God. Sorry. Yeah. The LightBox consists of trusted kernel and trusted application, and ShadowWatcher consists of trusted application and normal world application. The right part, ShadowWatcher client over there, collaborates with a LightBox and ShadowWatcher application in secure world through the SMC core. SMC core is the core part of the ARM TrustZone. So I hope to present shadowbox version 2 on platform at next security conference, and then the detailed information and full source code of shadowbox will be opened. All right. Conclusion. Yes. First, kernel-level threats should be protected in more privileged levels such as hypervisor. And second, shadowbox is lightweight and practical solution for protecting your kernel from rootkits. And third, real world is Serengeti, so you have a strong mentality for defeating the beast. If you don't have strong mentality, use shadowbox instead. Oh yeah, this is the last page of my presentation. Thank you for listening, and these are my email address and project link. Please search shadowbox for x86 at github.com. My project, Shadowfox, is open source, so I always welcome your contributions, such as bug report or code patches, and so on. If you have any idea about Shadowfox, feel free to email me. Thank you again. Oh, so any questions?
Thank you, Seunghun. Thank you. Any questions from the audience?
Hi.
Yep.
Do you use this Shadowbox on your own machines too?
Yep. This machine. Unfortunately, this machine is Mac, so Shadowfox, this version 1, only supports Linux distros, so you can use the Ubuntu or Fedora or something. Yeah.
You don't have a server that you run it on, for example?
Please say again. I cannot hear.
If you'd have a Linux server somewhere,
Linux server.
you could run a Shadowbox on it.
Yeah. Unfortunately, this version of Shadowbox targeted the desktop version of Linux distros. So I just only tested the normal desktop and the notebooks, not server.
Thanks.
Any other questions?
Thank you. Hi. So is it only for x86 as in 32 bits, or is it also for x86 64 or AMD 64?
Yeah, good question. This version of Shadowbox only supports x64, not x33. Yeah, x80. Yeah, yes. So 32-bit is not supported now. Yeah.
That was the last one? Any more? Thank you, guys. One more applause for Seunghun.